Welcome to the last section of the solutions unit, and that is going to be colligative properties. And it is a characteristic. There's certain things that are considered to be a colligative property that we'll talk about in a moment, but basically it is not dependent upon the size or type of particle, but on the concentration, okay? So the physical properties of solutions are different from those of pure solvent. For instance, salt water is a solution. The physical properties of salt water is different than pure water. The freezing point and melting point would be different. And that's because when I add this salt to it, it's got some particles. The higher the concentration, the more effect. So it's not really dependent upon the identity, but it's dependent upon how much of it, okay? It does depend on the number of particles. So the more number of particles, the greater the effect is going to be, especially if you're talking about two things of the same concentration. If one thing has more particles, it's going to have a greater effect. So before we go on to talk about those, let's talk about what a solution is. Of course, we've already discussed it's got a solute and a solvent. Okay, the solute is what is being dissolved. The solvent's what's doing the dissolving. And if you're adding a non-volatile solute to that solvent, it changes its colligative properties. And the way that it does that is it interferes with the phase changes for that pure solvent. Non-volatile is a word that basically means something that doesn't readily become a gas. So if I were to go back to that salt water example, salt obviously does not become a gas very readily, so it would be considered a non-volatile solute. Okay? So before we go on to learn the calculations, let's make sure we can count particles. This is very basic here. I know you know how to do it, but I would be remiss to not go over it. Remember, if we have a ionic compound that is soluble, when we dissolve it in water, it breaks apart into its ions. And so in this case, I would have sodium chloride would give me 2 particles, or we could even call those ions if you would prefer. And then sodium sulfate, because I have 2 and 1, that would be 3. And then ammonium phosphate, 3 and 1, would be 4 particles. Now, if you'll notice, the polyatomic ions count only as 1 particle. So they stay connected, okay? So they only count, unless you have a coefficient there, a polyatomic ion is 1 particle. Okay? Now, if you have a covalent or organic molecule, they do not ionize, so they stay together as 1 particle. For example, sugar, this is actually table sugars, it is 1 particle. It dissolves in water, as we know, but it does not break apart, so it would only count as 1 particle. And of course, the way we would recognize organic is going to be those hydrocarbons. There's going to be some carbon and hydrogen, and then of course, a covalent we're going to recognize as 2 non-metals. So if we see something like that, they're only going to count as 1 particle. Okay, so just to make sure we're going to do this, we're not going to do all of these because that would be redundant, but just let's do a couple of them real quick. Magnesium chloride would look like that, so that would give you 3 particles. Aluminum sulfate would be Al2SO43, that would be 5 particles. Iron 3 nitrate is going to be 4 particles. Ethanol, we've got carbon and hydrogen here, so that's only going to be 1 particle. And then dinitrogen pentoxide, that is 2 nonmetals, so that is covalent, so that would also only be 1 particle. So you have to be able to recognize that for when we get ready to do our calculations. Okay? So let's talk about what the colligative property is. I believe this, it got put back in your notes. Okay. So one of them that we're not going to do any calculations on, you just need to understand, is lowering the vapor pressure is a colligative property. Okay. So if I were to add a non-volatile substance, it would lower that vapor pressure, which means it would not become a gas as readily. Okay, so pure water, it would vaporize more quickly than if I put a non-volatile solvent in there. Okay, so that one you just have to understand the definition. The next two, you are going to have to know how to do the calculations. So this is what we call the phase diagram of water. And if you'll notice, the vapor pressure of the pure water would have a higher phase change for boiling point, but it would have a lower phase change for the freezing point when I add something in it. And so that's just kind of for you to see how it affects that phase change. So the first colligative property we're going to have to calculate is called the boiling point elevation. And that's going to be important to understand that when I put something in a solute, it will raise the boiling point, okay? So, and this is the calculation or the formula that you're going to use for that. I will tell you that KB is something called the Molal boiling point constant. I'm going to abbreviate point constant. So if it's a Molal boiling point, you know that little m is going to be molality of your solution. So that needs to know the concentration. And quite honestly, this is the only time we really use molality is in these calculations. And then I is something called the Van't Hoff factor, which is a fancy way of saying number of particles. Okay? And so we have to take that into account. All right? So I want to give you an example of boiling point elevation. Most of us have at least or seen, or if not done it ourselves, boiled water for some pasta. And a lot of people will add salt. And we ask, why do you add salt? And you'll hear things like, oh, well, it keeps it from sticking or makes it boil faster. And it actually does not make it boil faster because it raises the boiling point of the water. But what it does, because it's raising the boiling point, now you're cooking your pasta at a higher temperature, and so your pasta will actually cook a little faster. However, most people just put a little dash of salt in there. They just a little bit of dash and they're done. And honestly, the more salt you put in there, the faster your pasta will cook because it'll raise the boiling point even more because you're changing that concentration. So also, according to Rachel Ray, that's the only time you have to flavor your pasta. So I put quite a bit of salt in mine, actually. And so that is that formula for the boiling point. And guess what? For freezing point depression, it looks exactly the same formula with the exception of KF is, you guessed it, the Molal freezing point constant. Those are given to you. You do not have to memorize those. And every substance has its own constant. For instance, water has its own. If you look at this chart that you have in your notes, if you'll look at acetic acid, they have different KB and KF values, okay? The M still means molality. The I is still the number of particles. The difference is boiling point is an elevation. Freezing point is a depression, meaning it lowers the freezing point, okay? That's why we add salt to the roads when it gets close to freezing, because if we salt the roads, it lowers the freezing point of water, so now we're not having those icy roads at 0 degrees Celsius or slightly below, so it lowers that quite a bit, okay? So they're very easy formulas to use. The number one trick is we are calculating delta T for both of these boiling points or freezing points. So you'll see here in a second when we do this, we will have to either add or subtract from the original boiling point or freezing point. In the case of a boiling point, it's a boiling point elevation. So whatever we get delta T to be, we'll need to add it to the original boiling point. And if it's a freezing point depression, we'll have to subtract it because we're depressing it or lowering it, okay? So we have these 4 examples we're going to do real quick. All right, so we're going to use the chart that's in the notes for all of this. And it wants to know what is the boiling point of a solution in which 75 grams of sodium sulfate are dissolved in 800 grams. So we are doing a boiling point, so we're going to make sure that we add to our original boiling point. So we're going to use this formula, delta T, KB times M times I. So first thing I see is sodium sulfate looks like this, and that's going to give me how many particles? And that is 3. So I know that's going to be, which is going to be my I. I do not have my molality, so I'm going to have to calculate that. So I have 75 grams of the sodium sulfate. And I'm going to divide by the molar mass of that, which is 142.05 grams per mole. And then I'm going to divide by the solvent, which is 0.8 kilograms of water. So I'm going to get a molality of 0.66 little m. Okay? And I believe in your notes, the KB value, it is a typo. If you look at the chart, it's actually 0.512. It's not 5.12. So please cross that out and correct that in your notes. So then I'm going to calculate delta T now. And so I'm going to say 0.512. And notice the units are degrees C over molality. I'm going to plug in my molality. And I'm going to go back to that 3 and say that I have 3 particles. So my molality is going to cancel out. And that's going to give me a delta T of 1.01 degrees Celsius. Now here's where most common mistake is. They box the answer and say, I'm done. Does 1.01 make sense for a boiling point of water? No, it does not. And so we would say our new BP would be 100 plus 1.01. So the new boiling point would be 101.01 degrees Celsius. So that would be my new boiling point, okay? And now let's do a freezing point depression in the next example. In the freezing point depression, we're going to look at, this time we're not doing water, we're doing acetic acid. So make sure when we look at that chart, we get the right things for that. So again, magnesium bromide is MgBr2. So we're say I is going to be equal to 3 particles. Okay, so I've got 35 grams of magnesium bromide. I need to divide by the molar mass, which is 184.11. And then I need to divide by the kilograms of solvent, which is 0.4. And so I get a molality of 0.475 little m. And so now I'm ready to do delta T is equal to the Molal freezing point constant for acetic acid, if you look at the chart, is 3.9. Have my molality, right, of 0.475, and then it had 3 particles. So I get delta T is equal to 5.56 degrees C. That is not my answer. I need to figure out what the new freezing point is. And then I go look at my chart and I see that the freezing point of acetic acid is 16.6 minus 5.56. And so that would be 11.0. Honestly, we might as well make this 5.6 here so we can stay in one decimal place. So our new freezing point would be 11 degrees Celsius, and that would be our answer, okay? And before you start freaking out, you do not have to memorize this chart, with the exception of knowing the boiling point and freezing point of water. I do expect you to know that. KB and KF of water I would give you, okay? But you do need to know the boiling point and freezing point of only water. The rest of that stuff, if I want you to do something besides water, I will give you those freezing points and boiling points, okay? All right, we got one more, and this is a super easy one. This is just saying benzene solution boils, and it does say solution, so we're not talking about the pure solvent, boils at 87.3 and freezes at negative 1.2. Find the boiling point elevation and the freezing point depression. So basically, you're finding what is the delta T in a roundabout way. So for boiling point, the original boiling point is 87.3. Well, I mean, that's the new one, I'm sorry. And we're going to subtract out the normal boiling point of the solvent, and we would get that our boiling point elevation is 7.2 degrees C. And our freezing point depression, looks like Friendswood Police Department, doesn't it? Is the 5.4 is the freezing point, and we're going to subtract out the new freezing point, and we're going to get 6.6 would be the freezing point depression for that. Okay? And then one last, I was hoping to keep this under 15 minutes, but it's going to go a little over. I apologize. one last problem, and this is a challenge problem, and that is I'm going to figure out, based on my delta T, I'm going to figure out the molar mass of this solute, okay? So I don't know if you recall back when we were doing molecular and empirical formula, and we would get the percent composition and figure out what the empirical formula was, and then I would say, okay, this is the molar mass of this unknown compound. We never talked about, well, if they don't know what the compound is, how did they get the molar mass? This is one way they can do that. I can take a solvent and I can put an unknown substance in there, and I can basically figure out what the concentration, or what the molar mass is, okay? So it gives me the boiling point of the solution, and we're talking about a molecular solute, so that's a hint right there that I is equal to 1, and it's telling us what the boiling point. I've got 600 grams of nitrobenzene, okay? So I'm going to figure out what the change in temperature was. So the nitrobenzene is, we have a new boiling point of 214 minus 210.9. Let's do 10.88. Let's do that. And then I get a delta T of 3.12 degrees C. Okay, so that's my delta T. So I know that I have 3.12 degrees C is my delta T. I know that my boiling point constant for the nitrobenzene is 5.24. I do not know what molality is. That's what I'm going to solve for, and this is 1. Okay, so when I do my cross multiplying, my simple algebra, I'm going to get that I have a molality of 0.595. And so remember, when you see that 0.595, that really means moles of solute, right, over kilograms of solvent. That means the same thing. So it told me that my solvent was 600 grams. So I can say, okay, times 0.6 kilograms, and my kilograms cancels out, and that leaves me with 0.357 moles. Well, remember, molar mass is grams per mole. I almost did that backwards. That would have screwed us up. So it told me that I have 50 grams of this unknown solvent. So 50.0 grams divided by 0.357 moles, and I get 140.06 grams per mole. Now that's some fancy stuff right there, okay? Think about how far y'all have come from the beginning of the year to being able to do this kind of problem, okay? And that is the end of the lesson. All right.